Dear students, in this video I'll be discussing on the design of circuits with limited gate fanning. So what is this fanning? The number of inputs, the maximum number of inputs that we are going to provide to a gate. So these inputs are limited. It all depends on what type of gate we are realizing. When we are talking about the theoretical implementation of the things, so we keep providing any number of inputs for the gates, but when we are doing it practically, so the number of inputs for the gates are limited. As we already discussed related to the lab experiments, 7408 is a 2 input AND gates, 7432 is a 2 input OR gates. Suppose if we have only these components in order to realize the expressions, so then any problems whatever we need to realize, it has to be reduced to a 2 input. Then only we can able to implement using these components. So that's what we need to discuss today. So what is this gate fanning? It is the limited number of inputs for the gates. When this limited number of input, like the number of inputs required is more than whatever can be allowed, then we need to go with multi-level realization. So this will become mandate when the number of inputs are more than whatever is being allowed. For example, so we have already discussed the converting gray to binary, binary to gray. So this is a piece of conversion, like simplification of gray to binary. When we are converting gray to binary, we get these expression. So each terms is of 3 input AND gates. Suppose I want to convert this to a 2 input, and also the number of OR inputs are here 4. So but what we have in our lab is 2 input AND and 2 input OR. We need to convert this to 2 input AND and 2 input OR. How we can do this? So we take common out of these. So based on that we are going to reduce it. So for example in this, so G3 bar, G2 bar, G1. So then G3, G2, G1. So I'll take common G1 out of these two. So then I get this expression. Then out of these two I'll take G1 bar common. I get G3 bar, G2 plus G3, G2 bar. So now if you look into this, this becomes 2 input AND. This becomes 2 input AND. Then 2 input OR. So this and this 2 input AND. So here it is 2 input AND, 2 input AND, 2 input OR, then 2 input AND. This total term 2 input OR. So now this entire expression whatever was there before, 3 inputs AND and 4 input OR, now it's been converted into 2 input AND and OR. So now it is very easy to implement with the components whatever is available. This is what the gate fanning. So now we'll discuss an example on the gate fanning. So if this is the midterms given, using only 2 input NAND gates and inverters. So we can realize this function using only this constraints, 2 input AND gates and an NAND gates and an inverters. So first simplify this using a K-map. So in this example we have written the K-map in a different way. So we have written the max term here and the least significant here, most significant and least significant. So the cell values are like 0, 1, 3, 2, 4, 5, 7, 6. This is what the cell values. So we write the entries into the location 0 and into the location 1 it is 1. So 2, 3, 4 and 5. All these locations we put the entries, then do the grouping. So in this grouping, what the result we get is B bar, C bar. So that's what written here, B bar, C bar. And in this group, A, B bar, A, B bar. And in this group, A bar, B, A bar, B. This is what the result we got. When we look into this result, it is a 3 input OR gate. What we need is 2 input NAND gates. That's what we can use to realize this. So in order to make this to a 2 input, now we need to further simplify this, not simplification, what I can call it. So we can reduce this in order to make it a two inputs. So now we take a common out of this, B bar common. So A plus C bar plus A bar B. Now if you look into this expression, so this is a 2 input OR. Now this is 2 input AND. This is 2 input OR. So now whatever we have is a 2 input now. So you already know how to write equivalent circuit for this AND OR and the inverters also. But here it's been asked we can use the inverters, but the thing is we require 2 input NAND. So this is the equivalent circuit for the expression what we have obtained. So we have written using basic gates. Now what's been asked in the question is using only 2 input NAND gates. So we can use inverters. So we can retain these inverters, but we need to convert these AND and OR gate to an NAND gates. In order to convert this AND to a NAND, add the bubble to the front of it. In order to cancel the action of that bubble, we need to add one more inverter to the front of it. In order to convert this R to a NAND, need to write the bubbled NAND instead of an R. So that's what I'll write it, the next step. So I'll just write only these parts. So this is an inverter, and here I can make this AND to a NAND by adding an inverter to the front of it and one more inverter in order to cancel this action. This R can be converted to a bubbled NAND. So now this is B, this A. So we can just make this to a bubbled NAND. So I would have written this little before. So need to add it here. Then for C, need to add an inverter here. So this is C. This B, need to provide it to an AND gate. In order to make this AND to NAND, add bubble to the front of it. So this EA, I can have an inverter here. So this should go to this. This is what using NAND. But I can't write this bubbled, sorry, this bubble is missing. I can't write this like a bubbled NAND. In order to cancel these, so I can write one more inverter. So what I do is, in order to avoid one more step, I'll just cancel these bubbles. Now, these bubbles. So rest all will retain now. So what is the equivalent now? This is B. So I have an inverter here. Then NAND to the front of it. Then NAND to the front of it. This is how it is for the pth line. For A, this inverter, I need to write an inverter for A. Then one more NAND, whatever is here, connect to this NAND. Okay, it's been done. Now the second inverter and this has been cancelled. So directly I can provide C to this. Now B should be come and connected to this NAND. So I need to extract this B, give it to one more NAND, and this output should go, sorry, this inverter is there. So I need to implement one inverter and this output should go to this NAND because this inverter should be implemented. And for this CA, there is an inverter and then it's been connected. This inverter already it's here. So what I can do is I'll just extract this output, connect it here. That's it. So this circuit realization for this expression using 2 input NAND gates is done. So next we'll discuss the gate delay and timing diagrams. So whatever the gates we are implementing, so every gate will consume some time. So in order to process the input, whatever it is receiving. So what is the time consumption by any gates in order to process is called as an gate delay. So it's not in terms of a huge time gap. It will be very small time. It will be in terms of some nanoseconds. So we couldn't notice what is the time taken by the gates in order to process that. But when we measure, we can able to notice it. And when we have, just assume a circuit which is having some hundreds of gates. So whatever the processing time of every gate will be added together in order to find the final output. Then the output, whatever we are getting, it's not in line with the input. This is called as an gate delays. So the gate delay will affect the circuits majorly when it is a sequential circuits. So it's a less effect whenever it is a combinational logic circuit. The output depends only on the current inputs. Sequential circuits, output depends on the current inputs and the previous outputs. When there are more gate delays, so since the output is dependent on the present input and the previous output, there will be a major effect on the sequential circuits. So now we'll discuss the hazards in the combinational logic circuits. So what is this hazards? So we are expecting certain output, it's constantly, but for certain period of time there will be a change in the output, that is called as an hazard. So there are three types of hazards: static 1 hazard, static 0 hazard and dynamic hazard. What is a static 1 hazard? So we are expecting constantly, irrespective of the inputs, whatever we are providing, it's supposed to be 1 always. That's what called as in static 1. The name hazard because for some nanoseconds, because of the delay of the gates, it's changing its output to 0. That is what the static 1 hazard. Static 0 hazard. Constantly we are expecting 0 output, but certain period of time there will be a change in the output, that is called static 0 hazard. Dynamic hazard. So whenever we are expecting a change in state from 0 to 1, it will not change in one shot from 0 to 1. There will be a toggling between the states and then it will be settling into the expected state. That is called as an dynamic hazard. So it can be either from 0 to 1 change or 1 to 0 change. With this, I'll wind up this video. In the next video, we'll be discussing in detail on what is the static 0 hazard, static 1 hazard and how to cover it. Thank you.